So in today's session we will see that what is a latch, right? So we'll look at what is a latch from digital system design or digital logic design perspective. So if you see, latch is the fundamental memory block, right? So latch is the fundamental memory block. Right? So if you look at the basic latch, so the basic latch is an SR latch. SR latch. So this SR latch, it can be constructed either by using NOR gates, or it can be constructed either by using NAND gates. We will look at the construction of both of the design approaches, right? So the main thing is latch is the fundamental memory block, right? Fundamental memory block of sequential circuits, you can say. Also, if you see, there is no clock pulse present in a latch circuit, right? So there is going to be no clock pulse. Alternatively, you can also say latch is a level triggered device. What basically this means is, whenever the control signal is a high, right? Whenever the control signal is active, right? Whenever the control signal is active, the latch will be performing its function, and if the control signal is deactive, the latch will not be performing its function, or you can say whatever is the state that is previously stored at the output terminal, so it will be retaining that same state. So basically we can say no clock pulse is present in a latch, and also this is a level triggered device, right? Only at fixed value of, we can say, control signal, if at all, if it is provided to this circuit, it will work only when that control signal is active, right? So these are the fundamental points that we should understand first about the latch. After this, we will look at the circuit diagram for a latch, right? So if you look at the NOR implementation of a latch, so NOR implementation of an SR latch, right? Of an SR latch. So it is going to be, and also one last point is that there is going to be a feedback present in a latch, right? So feedback is present. So it is a fundamental memory block. It can be constructed either using NOR gates, NAND gates. No clock pulse is present. Loosely speaking, we can say latch is a level triggered device, right? It operates only when the control signal is active, and feedback is present in a latch circuit, right? Next, we'll look at the NOR implementation of an SR latch, right? How we can implement or how we can realize an SR latch using NOR gate. So if you see, we'll be using two NOR gates. So these are the two NOR gates, we can say. So this is going to be the output. This is going to be the output of this NOR gate. So we'll be providing one input to this NOR gate. We'll be providing one input to this NOR gate, right? With regard to the second input of the NOR gates, it will be present in terms of the feedback, right? So feedback from the output to the input. So if this is the output, then this is how the input is going to be there to this particular NOR gate. Similarly, if this is the output, so if you look at, so this output will be acting as the input to this NOR gate in terms of the feedback, right? So if if you look at this particular circuit, this is a basic SR latch with the help of NOR gates. So this is a basic SR latch. We call this terminal as the set terminal. We call this terminal as the reset terminal. We call this is the uncomplemented output, that is Q. We call this as the complemented output, that is Q bar. So this is basically a set terminal that we call. This is basically a reset terminal that we call. Why do we call this as set and why do we call this as a reset? So we will look into these details in the further part of this video. Next, if we look at the NAND implementation of a SR latch, so if we look at the NAND implementation, so if you look at the NAND implementation of an SR latch, so again we can understand it like this. So there are going to be two NAND gates. So this is the NAND gate 1, this is the NAND gate 2, right? So there is going to be one output out of this NAND gate, there is going to be one output out of this NAND gate, there will be one input present to this input of the NAND gate, there will be one input present at this input of the NAND gate. Next, if we look, since this is a latch, so definitely there is going to be a feedback mechanism. So the feedback from the output terminal will be there connecting the input of this NAND gate. Similarly, the feedback from the output will be there connecting the input of this NAND gate. After this, if we talk about the input terminals, then we represent the input terminals of a NAND gate as, so this particular input we call it as the S input, that is the set input. We call this input as the R input, that is the reset input. We call this output as the Q output, that is uncomplemented output. We call this output as the Q bar output, that is the complemented output, right? This particular arrangement is the NAND implementation of an SR latch, right? We also call this SR latch as S bar R bar latch, S bar R bar latch. We also call this particular arrangement of the latch implementation using NOR gates as the SR latch, SR latch. So why do we call this figure 1 as the SR latch, and why do we call the figure 2 as the S bar R bar latch? We will look into these details in the further sections of this video. So till now we must understand how do we perceive at this particular term, that is a latch. So latch is the fundamental memory block in the sequential circuits. There is going to be no clock pulse. If a control signal is there deriving the latch circuit, so that control signal or that particular circuit will be the level triggered device, right? Only when the control signal will be attaining its active level, during that state only that resultant circuit will be behaving as a latch. There is going to be feedback present. The implementation can be carried out using NOR gates and NAND gates. Figure 1 indicates the implementation of an SR latch using NOR gates, and figure 2 indicates the implementation of an SR latch using NAND gates. Figure 1 we call it as the SR latch, figure 2 we call it as the S bar R bar latch. Why the names are so, we'll look into it now, right? So if you look at the SR latch, right? So if we say the SR latch, And if we look at the implementation using NOR gates, so this is the implementation using NOR gates. So these are going to be the two NOR gates. So this is NOR gate, right? So this is the output Q, this is the output Q bar. This is one input that we call R. We call this as reset, and it will be clear, now that why do we call this as the reset input, and this is the set input. So if you look at the latch, so there is going to be feedback mechanism. So this output will be connecting this input of the NOR gate. This output will be connecting the input of this NOR gate, right? Now if you carefully observe this arrangement, so for this S and R, if we see, so S and R, these are the two inputs, and this output Q is there, representing the output terminal of this latch. So if you look at this S and R inputs, so assume that this S is having a value 1 and this R is having a value 0, right? In that case, we look what is going to be the value of this output Q, right? So initially, how we are going to proceed this discussion is, we'll assume that previously there is some value present at the output terminal, right? So initially, let us say some value when this circuit, it starts its function. Let us say previously the value of Q that is present is a 0. Just assume. So if previously Q is a 0, then this Q bar value is going to be 1, right? And what is the state of this S and R? So S is a 1 as we have taken for this particular case, and R is a 0, right? These are the inputs, right? Now if S is a 1, then this input is fixed to 1. If R is a 0, this input is fixed to 0, right? Now if you look at this Q bar input, so this is what 1. So from this feedback, it will be reaching to this particular end, that is 1. So this 0 from the feedback, it will be reaching to this particular input, and that is 1. So 1 and 1, what basically is going to be the output? So it is going to be a 0, right? So if you look, this 1 and 0, right? So these are operated with the help of NOR gate. So 1, 0, the NOR operation is going to be a 1, right? So the NOR operation of 1 and 1 is a 0. The NOR operation of 1 and 0 is 1. Now if you look at this particular one, right? So what we can say is that this is going to be what? The output 1, right? So this is 1, 1, 0. So what basically now happens is, this 0 will be made available to the input of this NOR gate, right? This 1 will be made available to the input of this NOR gate, right? So if you carefully see what you can say about the output of this 1 NOR 1, so it is going to be what? 1 NOR 1 is going to be a 0, repeating. So if you see, the output of 1 NOR 1 is going to be a 0. Similarly, if we look at the output of 0 NOR 0, so it is going to be a 1, right? So again, if you look, so this one will be there at the feedback input, at the input of this NOR gate, so this is a 1. So this 0 will be there at the input of this particular NOR gate, so this is 0. Now if you look at this 0 and this 0, since R is fixed to this 0 input, S is fixed to this 1 input, so 0 and 0, again it will result into what? It will result in a 1, right? And if you look at this 1 and 1, it will result in a 0. So what basically we can say is, due to this feedback mechanism, this output Q, it will always retain which value? It will always retain 1 value. Similarly, this Q bar, it will always retain which value? It will always retain a 0 value, right? So what we can say is, if previously is a 0, this uncomplemented output, and the complemented output is a 1, right? So if previously the output value is a 0, and if we apply the input S to be 1 and R to be 0, right? Then what basically happens is, irrespective of this value, right, if it is 0, it is going to attain a value that is 1, right? So we can say that when S is 1, R is 0, output is set, right? So output is what? Set. Next, if you consider, the second case, say for example, this is again the NOR gate arrangement, NOR gate implementation of this SR latch, right? So this is the NOR gate implementation of the SR latch. So this is the uncomplemented output Q. This is the complemented output Q bar. This is the input R that we provide to the input of this SR latch. This is the input S that we provide as the input to this SR latch, right? So the output terminals, if you see, these are connected with the help of this feedback mechanism, that is, this output will be connecting the input of this NOR gate. This output will be connecting the input of this NOR gate, right? Now in this particular case, we'll start our discussion by assuming that initially 1 is present, right? If you remember the previous discussion, here we have assumed that initially a 0 was present at the uncomplemented output. In this case, we will say that previously a value 1 is present, right? And now our circuit is ready to accept the input values, right? Previously the output is, since there is a feedback mechanism, so it will be attaining some fixed value. So we have assumed this time that this value is a 1. And what are the values that we have assigned to these inputs? So we have assigned the value S as 1, and we have assigned the value R as logical 0, right? Now if this is a 1, so this output Q bar is going to be a 0. So this is going to be a 0. Now this one, from the feedback mechanism, it will be made available to the input of this NOR gate. This 0 from the feedback mechanism will be made available to this particular NOR gate, right? Now if you look at this 0 and 0, so the output of the NOR gate is going to be a 1, right? If you look at this 1 1, so the output of the NOR gate is going to be a 0. Again, if you look at this 0, so from the feedback path, it will be made available to the input of this NOR gate. This one from the feedback path will be made available to the input of this NOR gate. Now if you look at this 1 and 1 NOR 1, so the output is going to be what? It is going to be a 0. It is going to be a 0. So if you look at this 0 and this 0, right? So if this 0 and this 0, output is going to be a 1, output of the NOR gate, right? This NOR gate. So again, this one will be made available with the help of this feedback mechanism at the input of this gate. This 0 with the help of feedback will be made available to the input of this NOR gate, right? So if you look at this 0 and 0, so NOR output of 0 and 0 is going to be what? It is going to be a 1, right? So this output is going to be 1 again. So similarly, this 1 and 1, the NOR output is going to be a 0, right? So basically what this feedback mechanism actually now doing is, it is always keeping the uncomplemented terminal, the output of the uncomplemented terminal, as a 1. And the output of the uncomplemented terminal is always going to be a 0. So what we can say is, if the value of S and if the value of R, right, if the value of S is a 1, logical 1, if the value of this R, it is a 0, that is, it is active low signal, then the output Q, right, whether previously it be a 0 value, or whether previously it be a 0 value, or previously it be a 1 value, if the inputs, they are set to 1 and to 0, right? If the input S is set a value active high, if the input R is set a value active low, then the output is always going to be attaining the 1 state, right, active high state. So output we can say it is set. So due to this reason, if you see, so due to this reason, we call the input S, right? We call the input S as what? We call the input S as the set input. Set input. So that is why we name it as the set input. Now, why do we call this R as the reset input? We'll see into this further section of this video. Why do we call this as R as the reset input? So this is the first case when input S is a 1 and input R is a 0. So the output, it is always going to be in the set state. Always it is going to be in the active high state. So next, if you look at the SR latch, right, using NOR gates, we'll see. So this was the implementation using NOR gate. So this is a NOR gate. This is again one NOR gate, right? So this is the output. This is the output of this. This is the input. We call it as R. This is the input. We call it as S. This is the output terminal connecting the input to this particular NOR gate with the help of feedback mechanism. This output terminal is connecting the input of this NOR gate with the help of feedback mechanism. This is the uncomplemented output we call. This is the complemented output we call, right? Now we will look at the case when the value of S is a 0 and the value of R is a 1, right? In this case, what is going to be the final value at the output terminal, that is Q. So we look at this discussion. So basically we can take this arrangement. Also we can consider the same arrangement in order to analyze for a different case for this same value of this S input and the same value of this R input, right? That is when S is 0 and R is 1. So these are two NOR gates. So this is the input R, this is the input S. So this output is connecting this NOR gate with the help of this feedback mechanism. This output is connecting the input of this NOR gate with the help of the feedback mechanism. This is the output Q, this is the output Q bar, right? So if you look at this, right, so what we can say is there can be only two possible conditions for this output Q. Either when this particular input S or when this particular input R, right, when the inputs are not active, either this value Q, it can contain a 0, or this value Q, it can contain a 1, right? These are only the two possibilities for this output Q. We'll start with this first possibility first, right? We'll say that previously the output value is the output value is containing a value logic 0, and now we will apply the input, that is we will apply the input S to be 0 and we will apply the input R to be 1, right? So if the input S is a 0, so what basically happens is this input is going to be fixed to 0. If the input R is 1, so this input is going to be fixed to 1. Right. So this 0 from the feedback, it will be made available to I'm sorry. So this 0 from the feedback will be made available to the input of this NOR gate, right? So 0 NOR 0, it is going to be a 1, right? So 0 NOR 0 is going to be, it is going to be 1. So if this is 0, so the complement output is going to be what? So if this is 0, we can say about the complement output that it is going to be a 1, right? So if this is a 1, so the input of this will be considering this one. So 1 and 1 is there, so NOR output is going to be what? It is going to be a 0, right? So what you can say about the output of this NOR gate, it is going to be a 0. Now if this is 0, from the feedback mechanism, it will be made available to the input of this. 0 NOR 0 is going to be what? it is going to be f1 again, right? It is going to be f1 again. So this one from the feedback made available to this particular input. So 1 NOR 1, it is going to be what? 0, right? So if you look at this 0, so from the feedback mechanism, it will be made available to this particular NOR gate, right? This 0 will be made available to the input of this NOR gate. So 0 NOR 0 is going to be 1. From the feedback, this 1 will be made available to the input of this. So 1 NOR 1, it is going to 0. So what you can say about the final output, this Q is always it will be retaining, it will be fixed at the value 0. Similarly, always it will be fixed to value 1, right? In which case the output is always fixed to 0 and always fixed, the complemented output is going to be fixed to 1 when the input S is a 0 and the input R is a 1, right? So this was one particular case for input S is a 0 and input R is a 1. Assume the second case when we are having the same inputs, that is R is a 1 and S is a 0, right? So R is, this input is a 1, right? Similar to this previous case, this input is 0. However, in this case, we will say that previously, right, before the circuit is active, this output is retaining some value, that is 1, logic 1, right? So we have assumed that before, the inputs are provided, the value 1 is present at the output of this Q. So Q bar is going to be what? It is going to be 0. So if this is 1, so from the feedback mechanism, so the input of this NOR gate is going to be F1. So this 0 will be made available to the input of this NOR gate, right? So 1, 0. So the NOR output will result into what? It will result in a 1 NOR 0. If you see, it will result in a 0, right? 1 NOR 0. Are you getting? So if this is a 1, so 1 NOR 0, that is going to be a 0. Now if you look at this particular output, so it is going to be 1 NOR 0 is going to be what? It is going to be a 0 again. It is going to be a 0. Now if this is 0, from the feedback it will be made available to input of this. So 1 NOR 0, if you see, and from the feedback mechanism, this 0 will be made available to the input of this NOR gate, right? So if we now look at this 0 NOR 0, so the output is going to be what? It is going to be F1. So if you look at this 0 and 1, so 0 NOR 1 output is going to be what? It is going to be a 0, right? So this 0 will be made available to the input of this NOR gate. So for the sake of understanding, we are writing this as N2, that is NOR gate N2. We are writing this as the NOR gate N1, right? So this 0 will be made available at the input of N2 NOR gate, right? So, and this 1 will be made available at the input of this N1 NOR gate from the feedback mechanism, if you see. Now if we carefully, look at the output of this N2, so it is going to be 0 NOR 0, so it is going to be what? A1. If you look at this 1 NOR 1, it is going to be what? It is going to be 0, right? Now again, if you look, this 0 will be made available as the input to this feed, this input N2, NOR gate, NOR input of N2. This one will be made available to the input of this NOR gate, that is N1, right? So 1 NOR 1, again it is going to be what? It is going to be 0. So 0 NOR 0, it is again going to be a. So what we can say is this particular uncomplemented output Q, it will now always set to the value 0. This uncomplemented one, it will always set to the value 1, right? So what basically we can say is, if the input S is a 0, right? If the input S is a 0, if the input R is a 1, so in this particular case, in an SR latch using NOR gates, irrespective of the previous value, right, that is present at the output terminals, whether the previous value may be a 0 or the previous value may be a 1, irrespective of this previous value, it is always going to set to a 0. Always it is going to set to a 0. And that is why we say that when the R input is 1, it is resetting the output, right? If R input is 1 and S input is 0, in that case the output is going to reset, right? We call this as the reset state, and for this reason we call the input R as the reset input, So if you see S is 0, R is 1, Q is going to be attaining the value 0, right? So that is why if you see, we have given the names to the inputs S and R as set and reset, right? That is why in case of a SR latch using NOR, we call the input S to be a set input. We call the input R to be a reset input. Because this input S, it is responsible for the final, output to fix to a set state, that is a logic 1 state. This input R is responsible to fix the output to a fixed state that we call as the reset state, right? So it depends. So if S is a 0, R is a 1, the output Q always it is going to be in the reset state. If S is 1 and R is 0, the output Q it is always going to be in the set state. So this Q is equal to 0 is the reset state. This Q is equals to 1 is the set state. And for this reason, we call the inputs S as set, the inputs R as reset, right? So this is regarding these two combinations of the input, right? Next, we will look at the another possibilities for the input in which the input S and R both are having 0 and 0 value. We'll see what will happen to the output in this particular case. So again, we will be taking two different possibilities for the output. So first we will construct this SR latch using the NOR gates. So we'll be taking the help of the NOR gate, right? So these are two NOR gates. This is the input terminal R. This is the input terminal S. This is the output Q. This is the output Q bar. Similarly, if you look at this particular arrangement of these NOR gates, so this is one NOR gate, this is the second NOR gate, this is the output Q, this is the output Q bar. This is one input of this NOR gate, that is R. This is the another input of the NOR gate, that is S. We call this NOR gate as N1. Just for the sake of understanding, we call this NOR gate as N2. This is N1, this is N2, right? Since we have to construct a latch circuit, then there is going to be a feedback mechanism. So this output Q, it will be connected to this N2 NOR gate as its second input in this feedback mechanism. This Q bar, it will be connected to this particular input of the first NOR gate, that is N1. Similarly, this output Q will be connecting the input N2 of this NOR gate. The output Q bar will be connecting the input of the N1 gate. So this is the input of the N1. In this case, we are considering that the input R is fixed, is provided a value 0. The input S is provided a value 0. This input R is provided a value 0. The input S is provided a value 0. Right. So similar to the previous cases, this output Q, it just have only two different possibilities. The first one is either it can previously be consisting of a value 0, or it can previously be consisting a value of 1, right? So we'll consider this possibility first. If previously, let us say q is a 0, this q bar is going to be then 1, right? So if this is a 0, then from this feedback mechanism, it will be made available to this particular input of the N2 gate. This one will be made available to the input of this particular N1 NOR gate. So 0 NOR 1, it is going to be what? It is going to be a 0. If you look at 0 NOR 0, it is going to be a 1, right? Now if we look at this particular one, right? So if you look at this particular one, so from the feedback mechanism, this one will be made available to the input of this N1 NOR gate. So if you look at this particular 0, from the feedback mechanism, it will be made available to the input of this NOR gate. So what we can say is that 0 NOR 0, it is going to be what? It is going to be a 1. And 1 NOR 0, it is going to be a 0, right? Now if you look again at the feedback mechanism, since the feedback is present, so what basically happens is, so this 0 with the help of feedback will be made available to the input of this NOR gate. This one with the help of feedback will be made available to the input of this NOR gate, right? So this one with the help of feedback will be made available at the input of this NOR gate. So 0 NOR 0 is going to be what? It is again resulting in a 0. And a 0 NOR 1, it will be resulting in a 0. 0 NOR 0, it will be resulting in a 1, right? And what basically we can say is, now due to the presence of this feedback mechanism, always this output Q is going to be retaining this value 0. Always this complemented output is going to retain this value 1, right? So what we can say is, if previously we are having a 0, right, and if we provide S and R inputs to be a 0 and 0, so even after providing these inputs, so we will be retaining this same value, that is 0. So the output Q, it will always be retaining this value, that is 0. It will be fixed at this particular level 0. Now we will look at this particular case when the previous value of the output is a 1, right? So if previously the output is a 1, so this output with the help of feedback mechanism will be made available to the input of this NOR gate. So if this is a 1, so this is going to be a 0. So Q bar is going to be what? It is going to be a 0. So from the feedback mechanism, this 0 will be made available to this particular input of N1. So it will be made available to this particular input of N1, that is 0. So 0 NOR 0 is going to be what? It is going to be 1. Again, this 1 NOR 0 output is going to be what? It is going to be a 0. Now what basically happens is, due to the presence of this feedback mechanism, so this 1 will be taken at the input of this N2. This 0 will be taken at the input of N1. 0 NOR 0, again a 1. 1 NOR 0, it is again a 0, right? Next, if you look at again the feedback mechanism, so this 0 will be taken at the input of this N1, 0. This one will be taken at the input of this N2, that is 1, right? So 1 NOR 1 is a 0. 0 NOR 0 is a 1. So what we can say is, always the output is going to be present in this 1 state or active high state. Always the output is going to be present in this 0 state or the active low state, right? So that is why if the inputs, right, if they are 0 and 0, if S input is 0, R input is 0, and if previously the value of the output that is present at the output terminal Q is a 1, so it will be retaining that same value, that is 1, right? So what basically we can say is, we can say that if S input is 0 and R input is a 1, right, so we can say that the output will be retaining its same value, that is Q. And this time we are incorporating this small subscript that is Qn plus 1, right? So this basically indicates that after implementation of these inputs, what is the output state. So this QN, it indicates whatever is the state of the output terminals before the application of these two inputs, that is 0 and 0. So right, if we apply these inputs 0 and 0, then the output will be retaining that same state, right? If previously it is a 0, then if S is a 0, R is a 0, and previously, right, before the application of these inputs, output is retaining a values, output is containing a value 0, right? Then after the application of these inputs, so the output will be retaining that same value, that is 0. Similarly, if inputs are 0 0 and previously at the output terminal Q a value 1 is there, so after application of these inputs, this Qn plus 1 is again going to retain this same value, that is 1. And we call this particular condition as the memory state or the hold state. Memory state or hold state, right? What basically this means is the output terminal will retain the same value which is present there before the application of these two inputs in terms of 0 and 0, right? That is S is 0 and R is 0, right? So this is how we can understand this third case wherein the inputs S and the inputs R, right? The inputs S and R. So if they are having a value 0 0, so in this particular case we call the output Q as what? We call the output Q as the memory or hold state. So if this Q we write in terms of this Qn plus 1, so we can also write this as this memory or hold, or we can write it as Qn. It will retain the same value. So this is going to be the third scenario for the inputs, right? Okay, now we will be considering the case when the input S and the input R both are 1. In this case we will see what will happen to the output, that is Qn plus 1, right? So we'll be considering two different, two same circuits for this SR latch using NOR gates. So this is one particular circuit. This is the input R, this is the input S, right? This is the output Q, this is the complemented output Q bar. Again, this is the NOR gate, this is the NOR gate, this is the output Q, this is the output Q bar, this is the input R, this is the input S, right? And since these are latch, right, both of the configurations are a configuration of an SR latch using NOR gate, so output will be connecting this input of the NOR gate with the help of this feedback mechanism. This Q bar will be connecting the input of this R, this particular NOR gate with the help of feedback mechanism. This is the feedback mechanism like this. This is the feedback mechanism like this, right? In this case, we are considering what? We are considering both inputs to be a 0 value, both inputs to be a 1 value, sorry. So R is going to be a 1, S is going to be a 1, R is going to be a 1, S is going to be a 1, right? So the outputs, they just have only two possibilities. Either before the application of these inputs, they can contain a value 0, right? They can be having this value 0. So if Q is 0, then Q bar is going to be 1, or this output Q, it can have a value 1, right, before these inputs are applied. So if Q is 1, then Q bar is going to be 0. So if Q is 0, so if from the feedback mechanism, this will be made available to this input of the NOR gate. We'll say this as N2, we'll say this as N1, right? Again, this is N1, this is N2. So 0 NOR 0, what is going to be the output? So 0 NOR 0, if we see, the output is going to be a 0, right? So this is 0 NOR 0, output is going to be what? A 0. Now if you look at this particular one, right, so 1 NOR 0, right, so 1 NOR 1 output is going to be a 0, right. Again if you look this 0, so from the feedback mechanism it will be made available to this 0 NOR 1, right. So since this S is 1, this R is 1, so 0 NOR 1 again is 0. From the feedback this 0 will be made available to input of this 0 NOR 1 again is 0. And you're getting, so what basically happens is in this particular case, right, again from the feedback mechanism 0 is there, from the feedback 0 is there, 1 NOR 0 again is 0, 0 NOR 1 again is 0, right. What basically happens is the output, both of these outputs, that is Q and Q bar, both are now fixed at the 0 value. However, the requirement of the outputs are to be complement of each other, right. Both of these outputs have to be complement of each other. So that is why we call such a state as what we say this forbidden state, right, or indeterminate state. So since this both of the outputs are fixed as 0, so we call this particular state as the forbidden state or indeterminate state. Indeterminate state, right. Similarly, if you look at the second case, when the output we assume that it is previously retaining a value 1, right, and now we are applying the inputs 1 and 1 at the input terminals S and R. So if previously this is a 1, right, so 1 NOR 1 is going to be 0, right. You look at this 0, since Q bar is 0, so this 0 NOR 1 it is going to be a 0. Again from the feedback this 0 NOR 1 it is going to be 0. From feedback this 0 NOR 1 it is going to be 0. From feedback this 0 NOR 1 input of this N2 result in a 0. From feedback this will be 0, input of this 0 NOR 1 will result in a 0. What we can say is that output will always be fixed to 0. Output, complemented output is always fixed to 0, right. So basically in this case as well, when previously there is value 1, the output is always fixed to what, this 0. Also the complemented output is fixed to what, 0, right. However, this is not the required, the state for these two outputs. So if Q is one output, then the other output Q bar has to be the complement of the other output, right. So since both of the outputs, that is complemented one and uncomplemented one, both of these outputs, that is Q and Q bar, are fixed to 0 and 0, even if previously if 1 was there, right. So that is why we call this as what, this forbidden state or indeterminate state. That is why we call this as the forbidden or indeterminate state, right. We also represent this with the help of this particular symbol, cross symbol, right. So also represent with the help of cross symbol. So if what we can say is, what we can conclude is, if both of the inputs of the SR latch, that is S and R, if both are equal to 1, then the output, that is Q and plus 1, right, that the output will be in the forbidden state, right. It will be in the forbidden state. We call this as forbidden state or indeterminate state. So how we can understand this particular case, if you see, so this particular case, when both of the inputs, that is S and R, when both of the inputs are 1 and 1, then the output, right, this Q is nothing but it is in the forbidden state, forbidden state or indeterminate state, indeterminate state, right. So this is how we should look at this particular case when both of the inputs are a 1, right. Now in order to conclude this SR latch using NOR gates, so if we want to conclude the SR latch using NOR gates, SR latch using NOR gates, NOR gates. So how we can conclude the operation of this as, so there are going to be the two NOR gates which will be connecting the output with the input of these NOR gates in the feedback mechanism, right? So these are going to be the outputs, that is Q and Q bar. These are going to be the two inputs, that is, we call this input as R, we call this input as S, right? So this is the set input we call, this is the reset input we call, right? And this output Q will be connecting the input of the NOR gate in the feedback manner like this. This output Q bar will be connecting the input of this NOR gate in the feedback manner like this, right? Apart from this, if you look at the characteristic table, so in the latches or flip-flop, we use the term characteristic table that describes the behavior of the circuit based on the inputs. So if S is one input and R is one input, right, and if Qn plus 1 is the state of the output terminal when the inputs are applied, right, it is the state of the output terminal when the inputs are applied. So there can be only four different possibilities. Either S can be 0, R can be a 0, S can be 0, R can be 1, S can be 1, R can be a 0, or both of the inputs are a 1, right? Or both of the inputs are a 1. These are the only four different possibilities with the inputs. So for all of these cases, if you see, once we apply these inputs, then the output in the first case, when S is 0 and R is 0, it will be retaining its same value which was previously present before the application of these inputs, right? So we call this state as what? We call this as the memory state. We call this as the memory or hold state, right? If S is 0 and R is 1, in this case, since R is 1, right, R is what? Reset input, S is set input. This particular case, when S is 0 and R is 1, output will always going to be in the reset state irrespective of its previous value. That is why we call this as the reset state, right? Irrespective of the previous value of the output, whether it be a 0 or whether it be a 1, if the input S is 0 and R is 1, it is always going to be present in the reset state. The output is always going to be resetted. If we consider the third case, that is if S is 1 and R is 0, right, if the set input is 1 and reset input is 0, in this case, irrespective of the value which is previously present at the output terminal, it is always going to be in the set state, right? So the output terminal is always going to be in the set state if S input is 1 and R input is 0, and that is why we call this as what? We call this as the set state. In the last combination of the inputs, that is when S is 1 and R is 1, this particular case we call this as the forbidden state, or we call this as the forbidden state, right? So we call this as the forbidden state or indeterminable state, right? Why do we call this as the forbidden or indeterminable state? Because both of the complemented and uncomplemented outputs, they are fixed to a 0 value, right? However, they have to be fixed to the values that are complement to each other, right? So if Q is 0, Q bar has to be 1. If Q is 1, Q bar has to be 0. However, in case when S is 1 and R is 1, the outputs, they both Q and Q bar, they are fixed to 0. That is why we call this as the forbidden state or the indeterminate state, or the indeterminate state, right? So this is how we should look at the operation of an SR latch using NOR gates. Also, if you see, we have used the word for the SR latch implementation using NOR gates as SR latch. We call this arrangement as SR latch, right? Because if you carefully see, the S input is a active, S input has to be what? An active high input in order to set the latch output, and the R input has to be a active high input in order to reset the output, right? So that is if S is active high, right? If S is active high, right, definitely R has to be a 0. In that case, the output is going to be set state. If R is active high, right, definitely S has to be a 0 in order to reset. So if R is active high, so the output will be in the reset state, right? So since the active high symbols are there, active high necessity is there for the inputs, that is S and R, in order to either set or reset the output. So that is why we call this SR implementation of the latch using NOR gates as SR latch. SR latch, right? Okay, and now we will see how we can realize a SR latch using NAND gate, right? How we can realize a SR latch using NAND gate. So this is the basic arrangement, that two NAND gates are present. The output of these NAND gates are connected in the feedback manner, right? The outputs are Q and Q bar. So Q is connected in the feedback manner to the input of N2. The other input of N2 is the input R. The Q bar output is connected in the feedback manner to the input of N1. The other input of N1 is a S. We call this implementation using NAND gate of SR latch, we call this as the S bar R bar latch, right? If you look at the characteristic table for this latch, if you see, so if S is the input and R is the another input, and if we consider that Qn plus 1 represents the output when we apply these inputs, then what is going to be the output state? So there can be only 4 different possibilities for the inputs, that is S is a 0, R is a 0, S is a 0, R is a 1, S is 1, R is a 0, and when both of the inputs are 1. So if these are the different values, then we will see in the further section of the video that if 0 inputs are there, we call this as the forbidden or indeterminate state. We call this as the forbidden or indeterminate state. If S is 0 and R is 1, we call this as the set state, that is output will be active high, so we call this as the set state. If S is 1, R is 0, we call this as the reset state. I'm sorry, that is the output will be in the active low state, right? We call this as the reset state. If both of the inputs are 1, so whatever be the value which is previously present at the output terminals, so the output will be retaining this same value, and we call this as the memory or hooked state of the SR latch using NAND gates, right? This particular configuration. Now if you carefully observe, the characteristic table, then what you can identify is, if S is 0 and definitely R has to be a 1, the output is basically in the set state. Are you getting? So the output is in the set state. So that is why if you look at the value of this S, it is active low. Similarly, if you look at the second case, when R is 0, that is active low, and S definitely has to be 1. So if R is active low and S is active high, the output is going to be what? Output is in the active low state, that is reset state, right? So if you look at the values of the input terminal, these are what? Active low. So S has to be an active low signal in order to set the output. R has to be an active low signal, right, in order to reset the output, right? So this is what? Set state. This is what? Reset state of the latch. And the inputs are what? These have to be in the active low states. So due to this reason, that inputs have to be in active low state, we call this SR latch implementation using NAND gates. We also call this as what? S bar R bar latch, right? That is why we call this as S bar R bar latch. If you look at the SR latch using NAND NOR gates, so in this case, the inputs S and R, they are in active high state in order to either set or reset the output. And for this reason, we call the SR latch implementation using NOR gates as SR latch, right? And there is small difference in the characteristic table for the SR latch using NOR gates. So the 1-1 conditions of the input, it results in the forbidden state. 0-0 result in the memory or the hold state. When R is 1, S is 0 will be the reset state. When S is 1, R is 0 will be the set state. However, in this case, when both of the inputs are 0-0, it results in the forbidden or indeterminate state. If both inputs are 1, it results in the memory or the hold state, right? If one of the input, that is R is 1 and S is 0, it results in the set state. And if one of the input, that is S is 1 and R is 0, it results in the reset state. How we can realize the functionalities for all of these 4 cases, we will now see in this particular section of this video, right? So if both of the inputs are, let us say 0-0, so we consider if S is 0 and R is 0. In this case, basically, what is going to be the output state? So if S is 0 and R is 0, right? So if any one input of the NAND gate, if it is 0, right? If this is 0, this is 0, right? So the input of this NAND gate is going to be 0. And also we know that if any one of the input of the NAND gate is 0, the output is always going to be 1. So that is one way we can understand that when both of the inputs are 0, so irrespective of these values, output are always going to be in the 1-1 state, right? Output are always going to be, so this output is always going to be in the 1 state, and this output is always going to be in 1 state, which is not a required state, right? These have to be complement of each other. So that is why, since the output Q and Q bar both are in 1-1 state, so we say we equivalently represent this output as the forbidden or the don't care state, right? So don't care or forbidden state or indeterminate state. If you want to verify the functionality using feedback, so you can understand. So if this is a 1, so from the feedback this has to be a 1. This is 1, right? If this is 1, what you can say about this Q bar? So it has to be a 0, right? So if this is a 0, so this is the feedback 0-0, output will be 1. So this one will be made available to the input of this N2 gate, right? So this 1 and 0, again it will result in a 1, right? This one will be made available to this particular input. 0 and 1, again a 1, right? So this one will be made available to the input of this 0-1, again a 1, right? This one will be made available at the input of this 0-1, again a 1. So always, if you see both of the these outputs, these are set to 1. If initially, let us say this Q is 1 and Q bar is 0, right? Initially, before we apply these inputs to be 0-0, so both of these outputs, they are set to a value 1, right? Since both of these outputs are set to a value 1, so that is why we call this as the forbidden or the indeterminate state. In the second possibility of the output, if we consider that, let us say that the output is having a value 0 before we apply S is 0 and R is 0. So if Q is 0, then Q bar is going to be 1, right? So this is 0, input of this is a 0, this is 1, input of N1 is a 1, 0, 1, NAND output will be 1. 0-0, NAND output will be 1. This is a 1, this is a 1, this is a 1, from the feedback this is 1, right? If you see 0 NAND 1, again 1, 0 NAND 1, again a 1. Again this one from the feedback, this one from the feedback, right? 0 NAND 1, again a 1, 0 NAND 1, again a 1. So basically the outputs, both of the outputs, these will be set to 1, right? Both of these outputs, they will be set to 1. But this is not a required condition, because the outputs have to be complement of each other. That is why we say the output as the forbidden or indeterminate state, if both of the inputs are a 0 0, right? If both of the inputs, that is S and R, they are a 0. So we represent it with the help of cross. We also call this as the forbidden state. We also call this as the indeterminate state, right? So if S and R both are 0, if S and R both are 0, we call the output to be in the forbidden or indeterminate state. We'll consider when S and R are 0 and 1. In this case, what is going to be the output? So if S is 0 and R is 1, S is 0 and R is 1. Either the output can be 0 or 1, or the output can be 1 or 0. So if we consider the first case, 0 NAND 1 will be 0 NAND 1 will be 1. And if you look at this 1, so 1 NAND 0 will be a 1. So this one from feedback, 1 NAND 0 will be a 0. This 0 NAND 0 will be a 1. Again 1 NAND 1 will be a 0. And if you look at this, this 0, so 0 NAND 0 will be a 1, right? So output is always going to be in this set state. The complemented will be in the reset. And this Q bar will be in 0 state. So what you can say that if S is 0 and R is 1, right? So Qn plus 1 is going to be in 1 state, right? Set state. If you look at this particular case, so this is a 1, this is a 1. So 1 NAND 1 output is going to be a 0. So this is 0. So 0 NAND 0 a 1. Again 1 NAND 1 0. 0 0 NAND 0 a 1. Output is always fixed to 1, right? So in this case we have seen if S is 0 and R is 1, the output is in set state, right? So that is why we can say if S is 0 and R is 1, the output is always going to be in the 1 state, and we call this as the set state. Now we will look at the case when S is 1 and R is 0. Then what is going to be the value for the Qn plus 1, right? So if S is 1 and R is 0, if S is 1 and R is 0, right, there can be only two possibilities for these outputs. Either it can previously be retaining a value 0, or it can previously be retaining a value 1. If this is 0, then Q bar is going to be 1. If this is 1, then Q bar is going to be 0, right? So if we apply the same concepts that we have discussed previously, then we can realize that if this is 1, that is S is 1 and R is 0, then the output will be always in the reset state, right? So applying the same, what we say, steps that we have followed previously using this feedback mechanism. So output Qn plus 1, it is always going to be retaining this value 0, right? It is always going to be in the reset state. So quickly, if you want to verify, you can verify it as well. So if this is 0, so this is going to be 0. Input is fixed to 0. 0 0, it is a 1. So this 1 will be made available to this feedback input. So 1 and 1, output will be 0. Again this 0 from the feedback, 0 0 1. This 1 from the feedback, 1 and 1 0. So output is always reset. If you look at this particular case, if previously Q is 1, right? So if Q is 1, so this is 1. So if this is 1, 1 0 output, and this is 0. So it is 0 previously. So when inputs 1 and 0 are there, so 1 0 will result in a 1. And this 1 0 will result in a 1. So this 1 will be taken to the input of this. So 1 0, right? And this 1 will be taken to the input of this, right? So this 1 and 1, it will result in a 0. And if you look this 0 and 1, it will result into a 1. Now this one again will be taken at the input of this. This 0 will be taken at the input of what we say this. So 0 NAND 0, 1, 1 NAND 1, 0, right? Again, if you look, this 0 will be taken input of this at the input of this 0 NAND 0, 1. right? This 1, if you see, it will be at the input of this 1 and 1 0. So what we can say about the output, it is always reset, right? So irrespective of the value which is previously present at these output terminals, this output when input S is 1 and R is 0 is always going to be present in, or is always going to be present in the reset state. So that is why we call this as the reset state of the output. Now we will look at the last case when both of the inputs are 1. In that case, what should happen, right? So if both of the inputs are 1, so if S is 1 and R is 1, S is 1 and R is 1. In this case, what will be the output? That is Qn plus 1. Qn plus 1 means the output when both of these inputs are present as 1. So before application of the inputs, let us say the output Q is having a value 0. This can be one possibility, or the output can have a output value 1. This is the another possibility. These are only the two possibilities for the output. So if this is 0, this is going to be 1. This is 1, this is going to be a 0. So this is 0. From the feedback it will be made available to this. From feedback it will be made available to the input of this N1. This is 1. From the feedback it will be made available to the input of this N2. This is 0. From the feedback it will be made available to this N1. Now we provide both of the inputs S as 1 and R as 1. The S as 1 and R as 1, right? Now we'll consider this first case. Now we will consider this first case, if you see. So if S is 1 and this feedback value is also 1, so the output is going to be 0. So if this is 0 and this is 1, so output is going to be 1. So if this is 0, from feedback it will be made available to this. This is 1, will be made available to the input of N1, right? 1 1 will be 0. 0 1 NAND will be 1. So again this 1 will be made available to the input of this N1. This 0 will be made available to the input of this N2. So again 0 1 output is 1, again 1 1 output will be 0. So what we can say is, if previously is a 0, so after the application of these two inputs, that is S as 1 and R as 1, output is still remaining in the 0 state, right? So if S and R, before the application of these inputs, if a value 0 is present at the output terminal, and if we apply the inputs to be 1 1, then after the application of these inputs, the output will still be remaining in the, the same state in which it was previously present. Now we will consider the second case in which the output is a 1, right? So if the previously the output is a 1, let us assume, then Q bar is going to be 0. Now we apply the inputs, that is 1 and 1. So if this is 1, so 1 1 NAND will be 0. So 0 1 NAND output will be 1. So this 1 will be made available to the input of this N2. This 0 will be made available to the input of this N1. So 0 1 again it is 1. 1 1 again it is 0. Again this 0 from feedback to the input of this N1 it goes. So 1 0 it will be 1. So, and if you look at this 1 1, the output is a 0, right? So again this 1 is there, so 1 1 again is 0, and again since this 0 is there, so 0 1 is again a 1, right? So what we can say is, if previously a 1 is there, right, and if we apply the inputs 1 1, then in that case output is going to retain that same value. So what we can say is, if before the application of the inputs, the previous value at the output terminal is a 1, and if we apply the inputs terminals, that is S and R, to be 1 and 1, then after the application of these inputs, the output will be retaining this same value. That is why we call this particular state, when the input S is 1 and input R is 1, as the memory or the hold state. We call this as the memory or hold state, because this Qn plus 1 is nothing but it will be retaining that same value which is present before the application of these inputs, right? So this is how we should understand the functionality of a SR latch using NAND gates, right? So this is how we should understand its functionality. So just in order to conclude this, So what we can say is, so we have seen this NAND gate implementation of an SR latch. So it will be consisting of two different NAND gates consisting of two inputs, that is S and R. The outputs Q and Q bar will be there, which will be connecting these inputs of the NAND gates with the help of a feedback mechanism. So output Q will be connecting the input to this NAND gate, and this output will be connecting to this input of the NAND gate, right? So this is the diagram of a SR latch implementation using NAND gates. If we look at the characteristic table of this, so what we have obtained is, if we are having the inputs S and input R, and if this is the output state of the output terminal when we apply these inputs, so there can be four different cases: 0 0, 0 1, 1 0 and 1 1. We call the 0 0 state as the forbidden or the indeterminate state, or indeterminate state. We call 0 1 as the set state. We call 1 0 as the reset state. Right. And we call 1 1 as the memory and hold state. Memory or hold state. So these are the four different cases that can be realized for this particular SR implementation using NAND gates. So this is a SR latch using NAND gates. Alright. And we call this particular implementation also as S bar R bar latch. So why do we give this name as S bar R bar? Because if you see, if S is 0, right, if S is an active low, definitely R has to be 1. If S is active low and R is active high, then the output is what? It is in the set state. Similarly, if R is active low and S is active high, the output is what? It is in the reset state, right? Since the set and reset of the outputs, it takes place on the active low conditions of this S and R, right? So that is why we call this particular implementation of SR latch using NAND gates as S bar R bar latch, right? So this is one thing. Now in order to make this S bar R bar latch equivalent to the SR latch, right? So in order to make the S bar R bar latch equivalent, right, S bar R bar latch equivalent conversion to an SR latch, right, we just do a small modification. That is, so we are having two NAND gates. So these are the two NAND gates, right? This is the output, we specify Q. This is the output, we specify Q bar, right? So what basically we do is, so this is the one input to this NAND gate. This is the another input to this NAND gate, right? And if we look at the output, so the outputs are connected. So the outputs are connected with the help of this feedback mechanism. These outputs are connected with the help of feedback mechanism, right? Now we just do a small modification, that we connect two NAND gates to this design, right? So if we connect the two NAND gates to this design, so this is NAND gate 1, this is the another NAND gate. So if we do this, just this small modification, right, and if we say that this NAND gate is connected to this particular input that we call as this S input, right, and if we call this particular input as the R input, right? And this circuit is operated with the help of this control signal, right? A control signal is provided. Control signal is there, right? So if this control signal is active high, it means this circuit is in operable state. It is in operational state, right? So if we do this modification, then it will result in a simple SR latch, right? So if you want to realize the characteristic table of this, you will be observing that S and R, right? S and R, if control signal is high, so if control signal is active, right? If control signal is active, then if you look at the S and R, if you look at the characteristic table of this particular SR latch, then what we can observe is 0 0 if the case, then output will be this will be retaining whatever the value previously present, right? So we call this as the memory state. 0 1 we call this as the reset state. 1 0 we call this as the set state. 1 1 we call this as the forbidden state, right? So this as the reset state, this as the set state, this as the forbidden or indeterminate state. Indeterminate state, and this is memory or hold state. So just by doing this small modification, by placing these two NAND gates in front of these two NAND gates, let us say N1 and N2, in front of these two NAND gates, that is N3 and N4, just if the N1 and N2 outputs, they are acting as the inputs to this N1, N3 and this N4 NAND gates, then it will be resulting in this equivalent SR latch. So this configuration, basically we can write it as SR latch. We can write it as SR latch instead of writing the S bar R bar latch, right? Because for this configuration, if S is what we say 1 and R is 0, then output will be reset, and if S is 0 and R is 1, output will be reset. So as in a summary, if we want to look at today's at this discussion, that then what we have seen is, what do we understand by a latch? So latch is nothing but the fundamental memory block in the sequential logic circuits. Latch can be implemented either by using NOR gates or by using NAND gates, right? So if latch is implemented using NOR gates, and if we are implementing it with the help of two NOR gates, if we are implementing with the help of two NOR gates, we call that implementation as SR latch. If we are implementing the latch with the help of NAND gates, and if we are using two NAND gates for the implementation, we call that implementation as S bar R bar latch. If we are using four NAND gates, we call that implementation as the SR latch, right? We call that implementation as the SR latch. So this is the basic implementation using NOR gates. This is the basic implementation using NOR gates: Q bar, S, R. So this is S, this is R, feedback, right? If you look at the implementation using two NAND gates, so two NAND gates will be there. So this is going to be S, this is going to be R, this is going to be Q, this is going to be Q bar. So this is feedback, this is feedback. This is the implementation using four NAND gates. If you are not using the control signal, we can represent it as S, we can represent it as R. Output will be provided to this NAND gate, output will be provided to this NAND gate, This is the output Q. This is the output Q bar. Will be connecting in the feedback manner to the input of this NAND gate. Will be connecting in the feedback manner to this NAND gate. So this is what? This is an SR latch. This is what? This is an S bar R bar latch. S bar R bar latch. And this is what? This is a SR latch. SR latch. If you look at the characteristic table for this, so if S, right, if you look at the characteristic table for this, so S and R, Qn plus 1, so 0 0 0 1 1 0 1 1 0 0 will be the memory state, 0 1 will be the reset state, 1 0 will be the set state, 1 1 will be the forbidden or indeterminate state. If you look at the characteristic table of this, so S and R, Qn plus 1, so if 0 0, it will be forbidden or indeterminable state, 0 1, it will be a set state, if 1 0, it will be a reset state, if 1 1, it will be a memory or the hold state, right? If you look at this particular implementation and the characteristic table for this, so S and R, if we look, then Qn plus 1, if you look at the final output, then 0 0 will be memory or hold state, 0 1 will be reset state, 1 0 will be the set state, 1 1 will be the forbidden or indeterminate state, right? So this is forbidden or indeterminate, state, right? So this is going to be the forbidden or indeterminate state. This is going to be the memory or hold state. This is going to be the reset state. This is going to be the set state, right? So this is all regarding the discussion, the detailed discussion for the topic, that is latch in the sequential circuits.